This is a very interesting question where the connecting string will have some mass. How to deal with this? Two blocks of mass m1 and m2 are connected with uniform rope of mass m and length L placed on frictionless surface as shown in the figure. You can see the diagram. Take end points of the rope is A and B. This is A, this is B, these are the end points. If a constant force F acts on the block, calculate tension at the point A and B. At point A, point B, how to find tension? Next one, find tension as a function of distance x from the point A. Let us consider distance from point A is x. Then we need to find tension at that point. This is the question. I'll make the diagram once again. We know that mass of rope is m. To deal with it, first let us consider entire thing as a single system. Mass of the total system will be m1 plus m2 plus m. This is the total mass. And on this, force applied is F. And if I write free body diagram of the system, I can write like this. Let us take total mass as capital M. Downward, capital mg. And upward, normal force. This is the normal force acting on total system, not on individual blocks. Normal force N and external applied force F, and there is no friction. Now we know very well the block will not move up and down, that it will move forward. If you apply Newton's second law, then you can write F is equal to capital M into A. So acceleration A is equal to F by m1 plus m2 plus m. This is the acceleration. Now we want to find tension at A. Now you see the way that we are taking the system. Right now our system is m2 and m. Observe, although our system is changed, mass changed, but still the acceleration remains same. So we can use the acceleration achieved in the previous segment as the same acceleration here. If I take the point A, what is the force acting on it? Definitely tension T. If I write the free body diagram of this m2 and m, we can write like this. Downward m2 plus m into g, upward normal force. Remember, this normal force is sum of normal force acting on the rope and m2. So let us call it as n1. And what force is pulling it forward? Tension at A, TA. If I write Newton's second law for this system, then I'll get net force is equal to mass into acceleration. So TA is equal to mass is m2 plus m into A. Let us consider this equation as 1 and put the value of acceleration from equation 1 in this equation. Now TA is equal to m2 plus m by m1 plus m2 plus m into F. This is the TA. This is part A. Let us continue with tension at B. To calculate tension at B, we take only mass m2. Now if you write the free body diagram, it will be like this. Downward m2g, upward normal force n2. Remember, this normal force is normal force only on m2. At this point, there will be tension that's called as TB. If I write Newton's second law for this, then F net action is equal to MA. So net force is TB. TB is equal to MA. M is M2 into A. Now we take value of A from equation number 1, we substitute. So TB is equal to M2 by M1 plus M2 plus M into F. This is the tension TB. This is part A. To solve part B, find tension as a function of distance x from point A. We'll copy the diagram once again. Then let us take a point on the rope, some random point. I'm taking this one, the red color point, and assume this point is at a distance of x from A. At this point, we need to take this entire mass. To find mass of this part of the rope, we use linear mass density of the rope. It's clearly mentioned that uniform rope, when the rope is uniform, mass per unit length, mass density will remain same. So total mass of the rope by total length of the rope must be equal to mass of this part of the rope, let us call this as m dash, by length of the rope, L minus x. This length is L minus x. So that implies m dash is equal to m by L into L minus x. Once we got the mass, we calculate tension at this point. To calculate tension at this point, we take this entire mass and we write free body diagram. Downward mg, that is m2 plus m dash into g. Upward normal force n4, and towards right tension T at a distance x, so let us call it as Tx. If you use Newton's second law, net force along x-axis will be equal to ma. So Tx is equal to m2 plus m dash into a, and we'll take the value of a from the equation 1 and we'll substitute here. Then we'll get Tx is equal to m2 plus m dash by m1 plus m2 plus m into f. Now we have to substitute the value of m dash from here and we'll get the answer. So Tx is equal to m2 plus m into L minus x by L whole divided by m1 plus m2 plus m into f. You can leave it here if you want to take LCM. Then it will be m2L plus m into L minus x by L into m1 plus m2 plus m. This is the value. If you want, you can cross check this one by applying boundaries. When I take x equal to 0, the answer must be TA. So put the value of x 0. When you make it 0, m2L plus ml by L into this one. So L gets cancelled. The answer will be m2 plus m by m1 plus m2 plus m into f. Check it, exactly matched. When you put x equal to L, then it must be tension at B. So you should get this answer. When you put x equal to L, this entire thing becomes 0. When this is 0, LL gets cancelled. It is m2 by this value. Exactly matching. Check it. This is how you have to deal with massive ropes.